Hello students, welcome to my lecture series on reinforced concrete structures. In this class, I am going to discuss about a complete design of singly reinforced cantilever beams according to IS 456-2000. The outcomes of today's class are, after completion of this class, you will be able to design a singly reinforced cantilever beams by considering all aspects like shear and anchorage length and all. So let us discuss what are the things we have discussed in last class. In last class, we have designed a singly reinforced, simply supported rectangular beam completely. And let me recall the steps what we did there. The steps are, first we have calculated what is that assumed depth is, or assumed overall depth. And from that assumed overall depth, we have calculated what is the width of the beam. And then we have, from the assumed overall depth, by assuming suitable cover, we have calculated what is the effective depth of the beam is. Then we have calculated effective length of the beam. Those are based on the two criteria. Among the first criteria and second criteria, first criteria is center to center distance between the beam, and then second criteria is clear span plus effective depth. The minimum of these two value will be taken as a effective span of the particular beam for a corresponding singly reinforced simply supported beams. And then we have calculated design loads, that is calculating dead loads and live loads. By adding together, we'll get the total load, then that will be multiplied with a suitable partial factor of safety, then we'll get the ultimate design load or maximum design load. Based on the maximum design loads, we have to calculate a design factor load, that is the maximum design load, and that from design load we have to calculate what is the factored bending moment is. After calculating the factor bending moments, we have to calculate what is the required depth for assumed depth and width of the beam. After calculating required depth, we have to compare the depth with the assumed depth of the beam. If the assumed depth of the beam is greater than the required depth, then we go ahead with that assumed depth of the beam for the further proceedings. Then we have to calculate area of steel required, the formula given as per IS 456-2000 code. So like that, we'll calculate what is the B, D and AST. These are the three parameters required. These are design parameters for any beams. Similar fashion, we'll calculate or we'll design today what is how to we'll design based on the same step a cantilever beam. So you know the cantilever beam is what is the definition of cantilever beam? The definition of cantilever beam is one end of the beam is fixed, another end of beam is free. So the best example for this, say your sunshades, chajjas, there comes under your cantilever beams, right? So to design those type of beams, I have taken some specification here. These are my required specifications. Based on this specification, I want to design what are my dimension of the beam and area of tensile steel provided, and and we have to give some checks for that so that our beam is safe against all aspects. Right? What is the basic difference between your cantilever beam and simply supported beam is? Generally, if you take a simply supported beam, if you take a cross section of that, we have a neutral axis at the center of that beam. Above the neutral axis there is a compression zone. Below the neutral axis there is a tension zone. Why you are saying it is a compression and tension? Because when you apply any vertical load onto the beam, the top fibers of a beam, simply supported beam, are under compression. That's why you can call it as a compression zone. And the bottom fibers, means below the neutral axis, the fibers what we have for the particular simply supported beam, those comes under a tension. So I can say the tensile zone. Now this case with the different in this cantilever beam. If we apply a vertical load onto a cantilever beam, the region which is above the neutral axis is tends to bend and tends under tension. That is under a tension. So above the neutral axis here we have a tension zone, and below the neutral axis the fibers of the beams are under compression. So we can call it as a compression zone. Finally, in cantilever beam, above the neutral axis we have a tension zone, and below the neutral axis we have a compression zone. We know that our concrete is very strong in compression, but it is weak in tension. So to counteract this or to fulfill this gap, that is weakness of tension of a concrete, there we have to provide reinforcement. So that's why we are providing a steel reinforcement in tension zone of the beam. So finally, in simply supported beam, tension zone will be below the neutral axis. In cantilever beam, the tension zone will be above the neutral axis. So in cantilever beam, we have to provide a main reinforcement above the neutral axis. Right. So let me see the specifications here. Here, when the effective span is equal to 2.5 meters, here directly has given effective span. No need to calculate the effective span separately as per IS 456 2000. That will be for according to the IS 456 2000. What is that value of effective span? That is span plus effective depth of the beam. That will give the effective span for cantilever beam. And he has given finally width of the beam also. Width of the beam also directly is given this problem. He requires 300 mm width and superimposed load of 20 kilonewton per meter, and finishes some extra load, that is 0.625 kilonewton per meter, and grade of concrete used is M20, grade of steel is used is Fe415. Right. So effective span given, width is given, superimposed load, that nothing but a live load is given, some finishes, floor finishes weight. So I can say it is a floor finishes weight, that is 0.625 kilonewton per meter, and width of the beam also given, that is 300 mm, and grade of concrete. From this grade of concrete we can calculate what is the characteristic compressive strength of a concrete, that will be denoted with the FCK. So FCK equal to 20 Newton per mm square. And here grade of steel is given Fe415. The designation of this is Fy, that is the yield strength of a steel. So that is 415 Newton per mm square, or I can call it the characteristic strength of a steel, that is Fy equal to 415 Newton per mm square. By using these specifications, now we have to design the cantilever, singly reinforced cantilever beam. So let is the first step, calculation of a overall depth. So here we can choose the overall depth based on the stiffness criteria of the beam. So what is the stiffness criteria here? Already we have discussed in our previous classes, that is some basic value for different kind of beams. So for simply supported, L by D ratio, this is called a basic value. The L by D ratio is 20 for simply supported beam. L by D ratio is 7 for your cantilever beam. Like that we have seen in our previous tables of IS 456 2000. So based on that criteria, that's called a stiffness criteria. Based on that, I want to choose what is the overall depth is. So for a cantilever beam, we have a L by D ratio, that is effective length to effective depth ratio is 7. This is called a basic value, and this is based on the stiffness criteria of the beam. So right here, so based on this, if I calculate what is the effective depth of this. So L equal to 70, from this D equal to L by 7. So you will have small d equal to L by 7. In the problem, the effective length of the beam is given is 2500, and the by 7, that will go 357 mm is sufficient. So effective depth required according to stiffness criteria is 357 mm. But anyhow, for factor of safety, I will adapt say 400 mm effective depth, and by assuming a cover of 50 mm, the overall depth will be 450 mm. As in the problem, it is given that B is equal to 300 mm. So finally, the assumed dimension of beams are effective depth is 400 mm, overall depth is 450 mm, and width of the beam is 300 mm. Anyhow, you got that effective depth based on the stiffness criteria is 357 mm, but we are not providing this, we are enhancing this value with some factor. So we are rounding up to say 400 mm. Nothing different, no problem with this. We provide extra means it will resist more loads, that's it. So next we go with that second step. Second step will be load calculation. So in a load calculation we have 3 different loads are given, that is dead load, that is sulfate we have to calculate, live load is already given in the problem, and a finishes load also given. So all together, if we add all those dead load plus live loads plus finishes, will we get what is the total load is. Then how to calculate this dead load or sulfate of the beam? So there is a formula, that is B width of the beam into overall depth of the beam into unit weight of RCC. Here the width of the beam is given is 300 mm, that is nothing but 0.3 meters, and overall depth is 450 mm. If you convert that into meters, that is 0.45 into 25. 25 is the unit weight of a concrete, that is in Newton per meter cube. If we multiply all those things, we'll get the dead load is 3.725 kilonewton per meter. And he has given imposed load. Imposed load is 20 kilonewton per meter, that is nothing but a live load also. and the finishes is given 0.625 kilonewton per meter. Now if we add all together, we will get total load, that is dead load plus live load plus finishes. Here dead load is 3.725 plus live load is 20 plus finishes is 0.675. If we add together, we will get 24 kilonewton per meter is the total load. This load is sufficient for calculating dimension of the beams. Whatever the dimension we have assumed, based on that the total load we have calculated is 24 kilonewton per meter. This load can be bared by this dimension of a beam, right? Then we have to enhance this load, so that by assuming some factor of suitable partial factor of safety that is given in this step. Calculation of design loads and moments for a cantilever beam with uniformly distributed load is factor load first we have to calculate. For calculating that uniformly distributed factor load, that is partial factor multiplied by total load. Generally total load we have calculated in the previous slide is 24, that will be multiplied with 1.5. We will get 1.5 into 24 equal to 36 kilonewton per meter. From this factor load we have to calculate what is the factor bending moment is. So the factor bending moment is WL square by 2 when a cantilever beam subjected to UDL throughout, then we get the maximum deflection at the free end, maximum bending moment at the free end, that is WL square by 2. Then W is 36 and L is 2.5 in terms of meters and kilonewton per meter. I am substituting here by 2. If we calculate this, we will get 112.5 kilonewton into meter or 112.5 10 to the power of 6 Newton into mm. So now we have calculated what is the factor load and factor bending moment. By using this, we have to calculate what is the required depth for particular load. So in this step, we have to calculate limiting moment of resistance. Why should we calculate this limiting moment of resistance is what is the definition of limiting moment of resistance? The moment of resistance of a beam calculated with respect to the limiting depth of neutral axis, that is a maximum depth of neutral axis, is called limiting moment of resistance. The purpose of calculating this limiting moment of resistance is to decide the type of beam section is. Generally, we have three types of beam sections. As already discussed those things in our previous lectures. Those are balanced section, under reinforced section and over reinforced section. So based on the values of factored bending moment and limiting moment of resistance value, the relation exists between these two, we can decide what type of beam section it is. Say we have mu is equal to mu limit, then we can call it as a balanced section. If mu is less than mu limit, then we can call it as a under reinforced section, and mu is greater than mu limit, then I can call it as a over reinforced section. So let's see our section, what type of section it is based on the data given. Right, this can be calculated, the limiting moment of resistance can be calculated as per IS 456-2000 as per given this table. Right, here per given the steel and grade of concrete and a dimension of the beam, we can calculate what is the mu limit is. Say in the problem, the grade of steel given is Fe415. For that we have to use this ready-made formula, that 0.138 FCK BD square. 0.138 FCK BD square. If substitute the values, that is 0.138. Here FCK is grade of concrete is that equal to 20, and B width of the beam is given is 300, and effective depth of beam we have assumed is 400, and so the square of that 400 square. If you calculate all these value, you will get what is the limiting moment of resistance is, that is 132.48 into 10 to the power of 6 Newton into mm. So let us consider, now we know what is the value of factor bending moment and what is the value of limiting bending moment. Let's compare these two values and establish a relation between these two values. So in the previous slide, in this slide we have calculated as a factor bending moment is, that is 112.5 into 10 power 6 Newton into mm, and here limiting moment of resistance is 132.48 into 10 power 6 Newton into mm. So here our limiting moment of resistance is more than the factored bending moment. So the relation exists is the limiting factored bending moment is less than limiting moment of resistance. So according to the condition what we discussed earlier, so this is fall under category of under reinforced section. So under reinforced sections are fails in due to failure of a steel. So it is a brittle, it is a ductile failure. So we have to calculate the moment of resistance of this particular section with respect to the tension zone or steel. Right. By knowing this mu and mu limit value, we have to calculate what is the required effective depth. So the depth assumed that the depth d equal to 400 is assumed depth. Randomly we have chosen, or based on the designer experience we have chosen. But now for a given dimension of a beam, what exact depth of beam is required? That we have to calculate by using these formulas that can be calculated by equating the factored bending moment or maximum bending moment to the limiting moment of resistance of the section. That is mu equal to mu limit. So mu equal to mu limit can be calculated by using this formula K equal to FCK BD square. This K value depends upon grade of steel. For different grade of steel, what will be the K value is mentioned below. That is for Fe250 it is 0.148, for Fe415 it is 0.138, and Fe500 it is 0.133. So if we substitute corresponding values in this equation, we will get the depth required small d is equal to under a whole root of mu is what 112.50, K is, as it is a Fe415 grade steel, the K the corresponding value is 0.138, FCK is grade of concrete, it is given 20 Newton for mm square, and width of the beam is given is 300. If we calculate that, we will get the effective depth required is 368.60 mm. Right. Now compare our assumed depth of a beam, that is assumed effective depth of beam, and calculated a required effective depth of a beam. If we compare those, the effective depth required, that is 368.60 mm, is less than provided, or I can say assumed depth. So we can go for further step, that is the provided depth is 400 mm. So our required depth is less than the provided depth, so no problem with that. Then we can proceed with the next step. Right. Next, with the previous slide, we have calculated what is the B value and what is the D value, that is width of the beam and effective depth of the beam. But for design of a reinforcing member means design calculation of area of cross section and amount of steel required in that particular section. These three parameters have to calculate. Already we have calculated two, that is B and D. Now we have to calculate what is the tension area of tension reinforcement is. So as I told you that the moment of resistance can be calculated with respect to tension, because we are providing steel in tension, and so mu equal to 0.87 Fy AST D into 1 minus Fy AST by BD into FCK. This formula is already we have discussed, and this same formula will be given in your code book also, IS, that is IS 456 2000. And the modification of this formula is this: directly AST we can calculate AST equal to 0.5 FCK by Fy into 1 minus under root of 1 minus 4.6 mu by FCK into B into D square, the whole multiplied by B into D. So what is the difference between these two formula that I already discussed in our, when we are designing a simply supported singly reinforced beams. So again I will explain here, no problem. So this, if you calculate the AST with respect to this formula, you will get a quadratic equation. The calculation of quadratic equation in a given limit of time, it is time consuming. So because of that, we have one more formula, that is directly we can calculate after substituting values, corresponding values in this formula. So here we will get a quadratic equation. Therefore for that we have two factors, and we have to choose as a positive factor or minimum factor as our AST. But here we will get a there is no factors, nothing, there is no solution of solving the equation here. So directly we can calculate AST by substituting Fy, FCK, Mu and BD values. So this is a little bit easy. I feel what I feel is this is a little bit easy compared to this equation. So my suggestion is to just remember this equation and substitute all those values and finally get the AST from this equation. So as you wish, you can use any one of the equation, no problem, we will get the same answer. So for this calculation, for this in this design of a cantilever beam, I have chosen the second equation. I feel comfort with this equation, that's why I have taken this. So substitute here 0.5 into FCK is 20, Fy is 4 and 5 into 1 minus under root of 1 minus 4.6 into Mu is 112.50 into 10 power 6 by 20 into 300 into 400 square, and whole multiplied by B into D. Sorry, the B is the 300 and D is the 400. Just correct it, please, dear students. This 300, and after calculating this, we'll get that area of tension reinforcement required, that is 927.9 mm square. Alright, now with this we have calculated what are the parameters required for the design of or a construction of your cantilever beam. So what are those parameters? B is the width, D is the effective depth, and AST, that is area of tension reinforcement provided in the beam. Right, whether the obtained values are really fulfill our criteria or they are really safe against the load applied. So for that we have to go for checks. So for that we have some checks here according to the IS 456. We will check for minimum area of reinforcement. That means for any kind of beam or any kind of slab, say now we are talking about beam, so we will limit our lecture to beams only. The minimum area of a tension reinforcement shall not be less than that given in the following. That means AS by BD is equal to 0.85 by Fy. So this is AS is minimum area of tension reinforcement provided in the beam. So the whatever the area of steel we have calculated previously, that area of steel should not be less than area of this. So let us check with our given specifications whether they are less than that or more than that. Say substitute the values, that is AS by, so 300 into 400. Dear students, again here some topographical mistake, please correct it. 300 into 400 by is equal to 0.85 by 415. After calculating this, we will get area of steel. The minimum area of steel provided in the tension zone is 245.7 mm square, that is AS, but our required AST is 927.9. so our minimum area of tension reinforcement provided is less than obtained area of tension reinforcement. So we can say we are safe in minimum area of reinforcement as we are providing more area than the minimum area required for the tension zone. So when we have minimum, again we have to check for maximum area of tension reinforcement also. For this also a code has given one recommendation, that is as for clause number 26.5.1.1 of B, there is a provision for that the maximum area of tension reinforcement shall not be exceed 0.04 times overall cross sectional area of a beam, that is small b into capital D here. Just correct this some topographical mistake. Small b into capital D. So small b is the width of the beam, D is the overall depth of the beam. The obtained value should be less than 4% of this BD. If it calculate 4% of BD with respect to this, that I will get 0.04 into 250, it is a 300, 500, and will get the value which is greater than 500 mm square. The value which is greater than 5000 mm square, just correct it, 5000 mm square, but anyhow the area calculated is 927.9 is less than the maximum value of tension reinforcement provided in the steel. So hence it is okay. The next one is spacing of the bars or number of bars provided. So how to provide this spacing and how to calculate this spacing. So spacing for this we have to assume a suitable diameter of bars, and what is the minimum diameter of bar will be provided in the beam, and what is the maximum diameter of bar can be provided in the beam, that according to your IS code IS 456 2000. For in this beam I will provide a diameter of bar is 20 mm. For calculating number of bars, that is AST required by area of 1 bar. So AST required is 927.9 mm square and area of 1 bar is 314. The number of bars can be calculated. AST required by area of 1 bar, that is 927.9 by 314, that equal to 2.955. So provide 3 numbers of 20 mm bars, and AST provided is 3 into 314 equal to 942 mm square. I think you got the difference between the AST required and AST provided. AST required is required amount of steel, already we are calculating according to the formula. So according to this, if I provide the steel number of bars, that is 2.955. So this fraction of bar we cannot provide in the actual practice. So we are rounding it to a higher value. So this, what is the higher value of this? 3 number of bars. So correspondingly, what are the number of bars and multiplied by single bar area that will I got is 942 mm square. That is actually what we are providing in the beam. That's why I can AST provided. Right. So now we have to check our beam whether it is safe against deflection or not. For checking that, we have to calculate what is the percentage of steel. The percentage of steel can be calculated AST 100 by AST into AST provided into 100 by BD. So that is 100 AST provided is 942, that we already calculated. B is 300 and D is 400. From this, if you calculate, we will get the area of steel. A percentage of steel is 0.785. As it not, please, it is cut it in the your notes. Say 0.785 percentage we will get, and you have to calculate the stress in steel under service load based on area of required, AST required and AST provided, and by giving grade of steel. So that formula is given in as per IS 456 2000. Fs equal to 0.58 Fy AST required by AST provided, that is 0.58 into 415 into AST required is 927.9 by AST provided 942. If we calculate, we will get that stress in steel under the service load is 237.6 Newton for mm square. So by obtaining these values, we have a one chart given, one graph given in the IS 456 2000. From that we have to calculate what is the modification factor. See, this is a graph. What is the component of this graph? On x-axis we have a percentage of tensile reinforcement. On y-axis we have modification factor. In between these we have some curves. Those curves are related to your steel stress of service loads, and that is corresponding to 290 Newton for mm square, 240 Newton for mm square, 190 Newton for mm square, 145 Newton for mm square, and 120 Newton for mm square. So in this problem, based on the data available or the specification given in the problem, we have calculated what is the Fs value and what is the PT value. From that we have to calculate what is your corresponding modification factor is. Say here I am assuming, say instead of 0.785 I am rounding up to 0.8 percentage of steel for our easy convenience. Nothing, we can choose approximately, right? So for that particular 0.8 percentage of steel, we have the curves for 190 and 240 steel stress of under service load, but we required for 237.6. so there is not exact value for that. So for that we have to calculate. We go for interpolation technique. From that we can calculate. So for that we required what is the higher values and what is the lower values of that, and we can calculate the in between value, that is 237.6 corresponding modification factor. So here if I want to calculate what is the modification factor for 190 Newton for mm square for a pointed percentage of steel. So 190, here it is somewhere in between 1.2 and it is 1.4 and 1.6. My modification factor will falls between 1.2 and 1.4. So I will choose the modification factor value approximately at 1.35. And similarly for 240 Newton for mm square, for the same percentage of steel, that is 0.8, the 240 corresponding to that, this is in between, say here it will come here. So it is 1 and it is 1.2. In between 1 and 1.2 my modification factor will be there. So for that I have chosen in between 1 and 1.2, say 1.15 is the value approximately I have chosen. You can choose any value between these two, there is no problem. For my convenience I have chosen these values, but the value should be within that limit only, not more than that and not less than that, right? So based on this, if I perform a modification, that interpolation technique for Fs equal to, that is 237.6, I will get the modification factor will be 1.16. So for 237, 1.156. So for this we have to calculate L by D maximum. L by D maximum means it is L is effective length of the beam and this D is effective depth of the beam, and what is the value of what will be the maximum value of this, that will be get the basic value multiplied by modification factor. The basic value for a cantilever beam is 7 and the modification factor what we have done is 1.16. So L by D maximum equal to basic value multiplied by KT. For that we will get 8.12. In no case our L by D ratio value should not exceed this percentage, that is this ratio, that is 8.12. So let what will calculate what actually we are providing in the beam. So L is the effective length of the beam, D is the effective depth. So effective length of the beam we are providing is 2500 mm and effective depth is 400 mm. If you calculate the ratio of this is 6.25. So our value is well below that maximum value. So L by D maximum is greater than L by D provided. Hence, I can say it's a OK. That means it is safe against the deflection. So this is how we can check for deflection of beams. Any beam, whether it is simply supported or cantilever or any continuous beam, we can check the deflection like this. Next, we have to calculate shear reinforcement. We have to go for shear design. So the shear design or the shear reinforcement or shear force value depends upon the type of condition, loading condition and type of support condition is. So a cantilever beam, now in this problem our cantilever beam is subjected to UDL and the maximum shear force occur at the support, that will be W into L. But we have to calculate what is the factored shear forces. So that will be multiplied with some value, that is W into L. Already we have W is a factor load and L is your effective length of the beam. If you multiply that, we will get 90 kilonewtons. So that is a factored shear force, 90 kilonewtons. Right. So according to this, we have to calculate what is the nominal shear stresses. So nominal shear stress as for class number 40.1 of IS 456-2000, that is tau V can be calculated by using this formula, that is tau V, Vu by Bd. Vu already we have calculated, that is 90 into 10 cube, that is in terms of Newton into newtons, and our B is 300, D is 400. If we calculate this, we will get 0.75 Newton for mm square. So next, we have to calculate maximum shear stress. Why should we calculate the maximum shear stress value? So whether really we go for a provision of or providing a shear reinforcement or not, that is based on the value of maximum shear stress and the relation exists between that nominal shear stress and the tau C max, that is a maximum shear stress. So this value, maximum shear stress value, is depends upon grade of concrete, and for particular grade of concrete in table number 20 of IS 456-2000, they are again some maximum shear stress values. So in this problem or in this design, I am using M20 grade concrete. For that corresponding maximum shear stress is 2.8 Newton for mm square. So if you compare your nominal shear stress and maximum shear stress, your nominal shear stress is less than maximum shear stress. So we can say that our section is adequate from the shear consideration. That means we can provide the shear reinforcement. So if the situation is different or reverse, if you get the tau V is greater than tau C max, then what will do? In this situation, we have to alter our dimension, that means we have to revise our dimension of beam and further we have to calculate. Right? It is in this case, in the design, our nominal shear stress is less than tau C max, so we can go for the further step. So I can say that it is adequate from the shear consideration. So for next we have to calculate percentage of steel. This percentage of steel already we have calculated, that is 0.8785. Here AST is area of tension steel, DB is the width of the beam and D is the effective depth of the beam. If you substitute all those values in this equation, we will get 100, AST is 942 by B is 300, D is the 400, we will get 0.85 percentage. Right. Next we have to calculate design shear strength. So what is the need of calculating design shear strength in this particular problem or any type of beam for providing shear reinforcement? Here we have two criteria for providing shear reinforcement. One is a nominal shear reinforcement, another is design shear reinforcement. Nominal shear reinforcement means if the value of design shear strength is less than the nominal shear stress, then we provide a nominal shear reinforcement according to the codal provision that is given in the IS 456-2000. If the value is different, if the nominal shear stress value is greater than your design shear strength, then definitely we go for the design. So for checking for that purpose, we have to calculate design shear strength of a concrete. Say here the different this value is depends upon the percentage of steel provided and grade of concrete of a grade of concrete which is used in the construction. So here this in the vertical direction we have a percentage of steel, and horizontal direction we have a grid of concrete. So the percentage of steel obtained is 0.785 percentage, and we are using M20 grade concrete. So here for this 0.8785% we don't have a particular value, but this value falls between the 0.75 to the 1. So by using interpolation technique we can calculate what is the exact value of design shear strength for corresponding to the 0.785% of steel. So from that, after using interpolation technique for M20 grade concrete and 0.785% steel, so we got the nominal shear, the design shear strength is 0.87 Newton for mm square. So if we compare your tau v value and tau c value, tau v is greater than tau c. We definitely go for design of the beam. So let's see how to design the shear reinforcement. So the shear reinforcement, how to design based on shear resisting capacity of a shear reinforcement. Say what we calculated so far is a factored shear force. That shear force has to resist by total RCC beam, but some amount of shear force is resisting by concrete, and remaining amount of shear force should be resisted by provided shear reinforcement. So we have to calculate shear reinforcement with respect to its resisting capacity. So that can be calculated by deducting the shear resisting capacity of a concrete from total shear force on the beam. So let us calculate what is the shear resisting capacity of a concrete. That is VC equal to tau c into BD. Tau c we have already calculated in the previous slide. That 0.87 into 300 into 400. From this we will get 68.4 kilonewton as a shear resisting capacity of a concrete. But our intention is to calculate shear to be resisted by shear reinforcement. How much of shear to be resisted by provided shear reinforcement, that we have to calculate. Say that will be designated with a VUS, that is shear force to be resisted by shear reinforcement equal to VU minus tau c BD. VU is the total shear force and minus tau c BD is the shear resisting capacity or shear force resisted by the concrete. If we deduct that, we will get what is shear resisting capacity of a shear reinforcement. That is 90 minus 68.4 will get 21.6 kilonewtons. For this 21.6 kilonewton, we have to design the shear reinforcement. So as our problem states that the relation exists between your nominal shear stress and design strength, it is tau v is greater than tau c. So we have go for design of that. So let us provide for this 8 mm diameter of two-legged vertical stirrup. So for this vertical stirrup, we have to calculate area of cross section for that, as we have a two-legged and we are using 8 mm diameter bar. So it is a circular cross section. For that we have a area of pi by 4 d square. In place of d, you have to substitute 8 as a diameter, and plus it is n means number of legs, for that is 2 legs. So area calculated for this stirrup is 100.5 mm square. Now we go for spacing. Also area we have calculated, that is well. And how much spacing we have to provide for calculated stirrups. So spacing can be calculated with respect to 3 criteria. The minimum of these 3 value will be provided as a spacing for the vertical stirrups. So spacing considered with respect to the shear resisting capacity of a stirrups, that is SV is equal to 0.87 Fy ASV into D by VUS. Substitute all those parameters already known to you. That is 0.87 Fy is 415 into 100.5 into 400 by, as we know that this VUS value is 21.6 kilonewtons. This I have converted into newtons. Then if we calculate this, we will get 671 mm. Spacing with respect to criteria is 671 mm. Next, spacing with respect to criteria B, that is with consideration of minimum shear reinforcement provided. So this is the formula for providing minimum shear reinforcement. According to this, we have to calculate what is the SV is. SV is spacing of a stirrup. That is, if we modify this formula, we will get ASV into 0.87 Fy by 0.4 into B. If we substitute the values here, that is 100.5 into 0.87 into 415 by 0.4 into 300. So if we calculate this, we will get the spacing with respect to the minimum shear force shear reinforcement consideration is 302 mm. The next is maximum allowed spacing. Here we have a two sub criteria, that is 0.75D and 300 mm, and minimum this minimum of this value will be considered as a maximum allowed spacing. So for this we have to calculate 0.75D. 0.75D into D is the 400, 300 mm. So 300 and less is 300 mm. So we have three criteria A, B, C. Among these three, the criteria C will give the minimum spacing. So provide 300 mm spacing between the stirrups. So finally I can say, hence provide two-legged 8 mm diameter stirrups at 300 mm center to center. So next we have anchorage length at support. So when you are providing main bars to form to transfer the bond stress onto the concrete, that some amount of length should be inserted into the column of a beam. So that length is called development length. So we can provide this anchorage length less or equal to that development length. For this particular problem, I am providing equal to that length. So I will calculate what the LD is. The development length of 20 mm diameter bar with M20 grade concrete and Fe415 steel is LD equal to 0.87 Fy 5 by 4 into tau BD. If sub phi is the diameter of bar, Fi is the grade of steel, and tau BD is the bond stress. This bond stress can be calculated based on this this table, which is given in IS 456 2000. But this table is corresponding to the limit state for plain bars in tension zone. But here in this problem, we are providing a bar in tension zone only, but the bar provided is Fe415, that is HYST bar. But bond stress of this type of bars provided in the tension zone can be increased by 60% to 60% more than the bars provided in a plain bar in tension zone. So in the plain bar tension zone, that is 1.2 for M20 grade concrete, that will be increased by 60%, so that is 1.6. So 1.2 into 1.6 will be the 1.92 Newton for mm square. If you calculate, if you substitute all these values in this LD equation, you will get 940 mm. So say I will take approximately 950 mm also. That means I had to provide the development length of 950 mm in straight bars and bent bars or U bends or whatever the possibility is there, that possible shape I can insert this development length as an anchorage length into the support. So let us see the reinforcing detailing. Here the main tension bar extended into the column up to a length of 350 mm. Say this is the main tension bar. Here this is the face of the column. After face of the column, I have inserted into the column up to 350 mm. After that, this bar will be bent into 90 degrees, but that is the length of the bent is I have provided 350 mm. So altogether approximately I will provide 950 mm of development length. Now tell me, what is the development length here? This total here to here. That is a minimum length which can be inserted. The reinforcement can be inserted into the section. Here section is column. So what is the function of this L bar here, LD here? So if you provide any tension for a tension force on this reinforcing bar, the tension force is trying to pull this bar out. But because of providing or inserting this bar into this column as in the form of a development length or anchorage length, that will hold your bar in position. So the stress induced due to imbalanced force will develop the stress in bond stress here. That bond stress is a stress induced at interface of your steel bar and concrete that will transfer the equal amount of load onto the concrete. So that is the purpose why we are providing LD or development length into this column. So this is all for today's lecture. Thank you.